Today's video is going to be a short discussion of radar cross-section. Radar cross-section, or RCS, is a measure of how much radar cross-section, or RCS, is a measure of the radiation power density received from a scatterer, a target, when it is illuminated by a radar. So consider this scenario. Let's say we've got a radar, some kind of antenna over here. That's its transmitter. And it sends an electromagnetic wave out, which encounters a scatterer. I'll use sigma to talk about the radar cross-section, although we haven't gotten to that point yet. Now this incident wave excites currents. So that would be current density J on the target. Next, those currents radiate. And they radiate in all directions. Not necessarily equally in all directions, but the currents that are excited on the body of this target don't necessarily result in radiation that comes straight back to the radar. Then we have our target. It has had currents excited on it. It is radiating. It's re-radiating that energy to some degree in all directions. And some of that energy comes back to our radar and is received. That's the scenario that we're talking about. The definition of radar cross-section is the area intercepting an amount of power which, if scattered isotropically, produces at the receiver a power density equal to that produced by the actual target. Now, I said that and wrote it down for you because it is convoluted and confusing and not a very well-worded definition. Here's what it really means. Let's work backwards. Some radiated power density, some scattered power density, is observed at the receiver. Then, what if this came from an isotropic source? In that case, the total scattered power would be 4 pi r squared, where r here is the distance between the target and the receiver, times that observed power density. Then, how much area is needed to collect that much power from the power density that was incident on the target. Like that. And because in general we assume that antennas and radars are far away from their targets, and a lot of things, which we'll talk about in later units of this class, depend on that simplifying assumption that things are far apart from each other. In general, you would take the limit as r goes to infinity of this expression. So really, it is sigma is the limit as r goes to infinity of 4 pi r squared ws over wi. Wi here doesn't change as r goes to infinity, but 4 pi r squared ws is basically canceling out the position dependence of the scattered power. It's important to note, I have one last thing to say about radar cross-section. Often the radar cross-section sigma is reported as a scalar, especially for monostatic situations. But it is not a scalar really. It really depends on the angles of incidence and of the angle of observation. So it depends on angle of incidence. That is, where is the incident, the wave from the transmitter coming from the target's point of view, and angle of observation. Where is the receiver from the target's point of view? So most generally, the radar cross-section of an object is a function of the direction to the transmitter and the direction to the receiver. Actually, calculating the radar cross-section is well outside the scope of this class. This is an undergraduate antenna class, not a graduate level electromagnetics class, so we're not going to talk about that, but I wanted you to fully understand how the radar cross-section is defined and what it means for radar systems.